Okay, so we'll start this here. Being normal, nah, that's overrated. We're going to talk about normal force. So this is one of those weird things. I really like this physics book. I like the way they lay out most of the concepts. The one beef I have with them is that they introduce normal force 3/4 of the way through chapter 4, and you need to know it now. So we're going to talk about normal force now because the first problem on the worksheet is a normal force problem. So what is normal force? It's the thing that's keeping you out of Mrs. Berger's room right now. Where is Mrs. Berger's room? Everybody point. Directly below us. And if it were not for the normal force that the floor is exerting on your chair, you would be sitting there, not here. So I have some object. It has some force of gravity downward on it. And that force of gravity downward on it happens to be equal, and we'll do a lot more of this when your chapter decides to introduce it, but I'm going to give you the preview version. Happens to be its mass in kilograms times g, mg. So you can figure out what the force of gravity downward on you is if you know your mass in kilograms. You multiply it by 9.81 meters per second squared, and you get the force of gravity down on you. Now, if you are still sitting in your chair and you haven't sunk through the floor yet, that means that the chair is exerting a force upward on you equal and opposite to the force of gravity downward on you. And we have a special name for this force. It's normal force. And it is shown with a lowercase n. Lowercase, look it up. I always get confused. I'm pretty sure it's lowercase. It's not the biggest problem we have usually. Normal force comes upward from a surface, period. If an object is not on a surface, there is no normal force on it. Let me repeat that. That's going to be important in the second part of our little talk. So normal force comes upward from a surface. You've got a calculator laying on your desk, you've got a pencil laying on your desk, you've got a book laying on your desk. All of those things have a force upwards on them from the surface. That is the normal force acting on them. In the absence of all other forces, normal force is generally the same magnitude as gravitational force, but in the opposite direction, on a horizontal surface with no other forces in the picture. The calculator that's laying, I'm looking at a few calculators. The calculator laying here on the desk has no lateral forces, no side-to-side forces. The desk is not sloped. Normal force there is going to be equal to the force of gravity downward on it. We will get into cases where normal force is way more complicated than that, but that's okay. The big thing I want you to understand is that normal force is perpendicular to the surface. Normal force is always perpendicular to the surface, period. Doesn't matter how the surface is oriented. That's important. And I'm mentioning this and I'm stressing this because I think I didn't stress it enough at one time in teaching this, and then I would have people doing their normal force wrong. So I'm stressing this, talking about it. We're hearing this. So let's show an example where normal force is perpendicular to the surface, but it's not straight up in the air. Nice flat surface, nice horizontal surface. Normal force is straight up in the air. Gravity is straight down into the ground. What the heck, even though I gave away the punchline, I'll go ahead and ask you, does that mean that normal force is always directly up? No, of course not. What if I have an object on a slope? We do a lot of these. The normal force is perpendicular to the surface. It looks like that. Gravity is not perpendicular to the surface because gravity doesn't care about your stinking, slidey, slippy, slopey surface. Gravity only cares about your relationship to the center of the earth, and gravity is always going to be straight down. Normal force is always going to be perpendicular to the surface. So, questions, comments, concerns?